Hey everyone, in this video what we want to look at is this idea of conserving momentum in more than one direction. We saw this a lot in the bubble collisions, so I want to highlight what we were supposed to see. That momentum is conserved no matter what. No matter which way you're moving, the momentum before a collision must be the same as momentum after the collision. So that means that all your x momentum in the beginning has to be equal to all your x final momentum at the end. So no matter how the scenario works, that always has to match up perfectly, x, y, or z. So you can keep the momentum separate, you can put them as one velocity that is heading off at an angle, but for simplicity it might be easier just to keep the x momentum separate from the y momentum, separate from the z momentum. So here's our scenario. We've got one car moving to the east, one car heading to the north, and they collide and hit and stick together. The question is, what is their V final when they head off in this direction? So let's give some values. Okay, so in looking at this, we've got the big car at 100 kilograms, the small car at 50 kilograms, but they're both going the same velocity. So when we do this, we want to make sure that all our momentum before a collision and after a collision are the same. So if you look at, we'll call this the green car. The green car's momentum is easy to calculate. It's 100 multiplied by 4, so there's 400 kilograms meters per second in the green car. That momentum is all towards the east. So that means after the collision, that green momentum has to stay the same. So this momentum here has to equal 400 meters per second. Let's look at the bottom car. The bottom car is heading north, and we'll say that the blue momentum here is 50 times 4, or 200 units of momentum towards the north. So that means that after the collision, we must conserve 200 kilograms meters per second towards the north. So if I want to find out the net sum of that collision, we need to do 200 squared, 400 squared to find the net momentum off in that direction. So doing that calculation, you get a net final momentum of 447 kilograms meters per second. That's made up of your momentum to the east and your momentum to the north. If you want to solve for your velocity, just know that momentum simply equals mv to find your v final, and this mass ends up being the mass of both cars combined together, since they did hit and stick. If they bounce apart like we saw in the videos, then you must keep their momentum separate for each object. So if I want to solve for a final velocity here, I take my 447 kilograms meters per second, divide by my total mass of 150, and you get approximately 3 meters per second off to the northeast. To find out exactly what angle, you're going to have to do some trig there to figure out exactly where this car is going to go. So it's not going to go to perfect 45 because they have different values of momentum. More momentum to the right than they do going up. So let's look at another scenario for colliding at angles. Okay, in this example here, we've got a ball, mass 1, coming in. Ball 2 is sitting there at rest, so the momentum in the beginning is very, very easy. It's just m1v1 plus 0 momentum for the second object, so all the momentum is in mass 1, and all of this momentum is in the x direction. So let's look at the end collision. After the collision, mass 2 goes off at an angle of theta 2, and mass 1 goes off at an angle of theta 1. Well, if you look at that, that means that there's velocity in the x for both, and there's velocity in the y for both. But how can that be? In the beginning of the problem, all our momentum was in the x direction, and now we have momentum in the x and y direction. Well, we have to conserve both directions. So the way we could write that is saying that all my momentum in the x direction originally now equals m1 v1 cosine plus m2 v2 cosine. So that original x momentum is now split between both x momentums for the angled shot. But let's look at the y direction. The y direction had no momentum to begin with, and in the end we've got 2 y momentums. But you gotta remember, momentum's a vector, so really this is how you want to write it. So m1 v1 sine theta 1 minus m2 v2 sine theta 2 will get you the conservation for the y direction. So things you might be given the starting mass and the starting velocity. You might be given one of the angles that they go away at, or if they don't give you that angle, what you can do is substitute and solve. Or if they give you one velocity, they'll want you to calculate for the other velocity. So I'll let you work through that and make sure when you're proving momentum conservation for angled collisions here that they do conserve momentum in the X direction and the Y direction. So here's one with numbers. Go through in this, and it looks like they want you to figure out the velocities of both pucks. One's coming in at 5 kilograms and 2 meters per second. The other puck, I assume, is also 5 kilograms and is heading off at 30 degrees. And if you look, V2 is heading off at 60 degrees. So when you have an angle collision, when two things go off at two different angles, they sum to 90 degrees. Because if you think about it, if you hit at 0, you'll just move straight at 0. If these two masses hit around 90 degrees, they would miss each other completely. But if there's any glance in a collision, that angle should sum to 90 degrees when those two objects collide. So we could put back in our numbers back into the problem we just did, and since both objects have the same mass, we can really knock out the masses all the way through, and we know that our starting velocity of 2 must equal v1 cosine theta 1 and v2 cosine theta 2. Okay, but we don't know v1 or v2, so you can come down to the y direction and again cancel the masses since they're both the same mass, and then solve for v1 or v2. If I solve for v1, so you end up with v2 sine theta 2 over sine of theta 1. You're going to put v1 back up into your x direction, and now you have an equation all for velocity 2. Once you get velocity 2, plug it back in the other way to solve for both velocities. Again, any of these glancing collisions, you can see that when they do collide, they do separate at a 90-degree angle. So if you're given one angle, you should know the other angle after the collision by just doing 90 minus. So the last idea here is using relative velocity when you're talking about a collision problem. Or if we talk about the speed of approach of two objects versus the speed of recession. So how fast they're moving with respect to each other as they collide, and how fast do they pull away from each other when they move apart. If the speed of approach equals the speed of recession, we get a value of 1 for our coefficient of restitution. And when we have a coefficient of restitution of 1, we know that energy or momentum is conserved and we have a fully elastic collision. If the speed of recession is 0, that means the two objects have hit and stuck together. And when they hit and stick together, that means that both objects are going the same speed. They are not pulling apart from each other after the collision. So the coefficient of restitution here goes between 0 for a perfectly inelastic collision and 1 for a perfectly elastic collision. Any fraction in between is that inelastic collision that will have momentum conserved but energy lost. You see this, you see v1 and v2. How fast are they approaching each other? Let's put some numbers to this. We'll say that v1 is 5 meters per second, v2 is 2 meters per second. So that means that the speed of approach is 3 meters per second. Mass 1 is catching up to mass 2 at a rate of 3 meters per second. They're going to collide, and let's say that the elasticity is 1.0. That means my speed of recession has to equal 3 meters per second. So if we end up doing this, we look at mass 1 and mass 2. Mass 2 is going to gain some velocity and mass 1 is going to lose some velocity. So if that's the case, if mass 1 drops to 2 meters per second, that means that mass 1 drops to 2 meters per second, mass 2 must gain that extra 3 meters per second and leave faster than mass 1 is approaching it. If that coefficient of restitution is anything less than 1, then you can figure out the speed of recession. If you know one of the velocities afterwards, you can figure out how quickly they're pulling apart. But again, momentum will be conserved, energy will be lost. So back to the simulator here. We've got two masses. We'll have them be the same mass. Orange velocity at 1 and blue velocity at -2. We'll set the collision to happen. This is an elastic collision. And there is our end results. The orange velocity moved to -2. The blue velocity moved to +1. They basically swap velocity since they were even masses. Let's change the masses up. So now orange mass is twice as big as it was last time, and now you can see that it has a completely different velocity than it had last time. So now it's going backwards at -1, and the blue cart is moving back to its original position at +2. This is an elastic collision. The coefficient of restitution should match up perfectly. And since it's elastic, let's prove that the kinetic energy is the same before and after. Okay, so we saw that the momentum was conserved. Let's prove that it is an elastic collision by conserving energy. All we have to do is add up their kinetic energies. So here's my energies before and after the collision. You can see on the left side I have my kinetic energy of both objects before, and on the right I have my kinetic energy of both on the back end. If I do the first one, 1 squared is 1 times 2 is 2, half of 2 is 1. So there's 1 joule of kinetic energy in the orange cart. In the other cart, that's -2 squared, which gives you 4. Half of 4 is 2. So I've got 3 joules. So I've got 3 total joules of kinetic energy before the collision. If you look at the math afterwards and you add those up, I'm going to get 3 joules of kinetic energy after the collision. Since energies are the same, we're going to have them be an elastic collision. And the speed of approach here, speed of approach is 3 meters per second because they're heading at each other. And the speed of recession is still 3 meters per second because now they're leaving each other at that 3 meter per second rate. So we know it's a perfectly elastic collision, energy was conserved, and the coefficient of restitution added up to 1.